It's really important for scientists to strive for accuracy when we're taking our measurements. Accuracy is the closeness of measurements to the correct or accepted value. The density of aluminum is 2.7 grams per cubic centimeter. That's the accepted value. This little guy is made out of aluminum, and if I wanted to determine its density by taking the mass and the volume and dividing mass by volume, and I got a density of 2.7 grams per cubic centimeter, then I would be very accurate. Precision is a little different. It refers to the closeness of a set of measurements of same quantity made in the same way. If I'm to measure something on an electronic balance, the first thing I need to do is tare it, which sets the balance to 0. Let's say I want to mass this 200 gram weight, but I forget to tare the balance. My first measurement is 197.1 grams. The second time I mass this 200 gram weight, I get 196.9 grams. And then I take a third measurement and I get 197.0 grams. And those measurements are all very close to each other, so they're very precise. But remember, it was a 200 gram weight, so my measurements were not really accurate. It might be easiest to think about this as accuracy means I'm getting the correct measurements. Precision means I'm getting consistent results, although they might not be the correct results. In the lab, we're going to strive for both accuracy and precision. When we work in the lab, we like to compare our results to the results that we should have gotten, or the accepted value, and there's a formula that we use to do that. Percentage error is the theoretical value, what we should have gotten, minus the experimental value, what we actually got in the lab during the experiment, divided by the theoretical value. And we take the absolute value of all of that, multiply it by 100. We take the absolute value so that regardless of whether we get a positive or a negative value, we'll look at it as positive value. We want to know how far off we are from what we should have gotten. Let's go back to our little aluminum guy. The density of aluminum is 2.7 grams per cubic centimeter. When I took a piece of aluminum into the lab and measured the mass and the volume and calculated the density, I got 2.4 grams per cubic centimeter. That translates to a percentage error of 11.1%. There will always be some error or uncertainty when we obtain measurements. That could be due to human error, or it could be due to the measuring instruments themselves. This is a beaker. Beakers are really not measuring devices because you just can't get accurate measurements from them. I'm really not sure if this is 49 milliliters or 48 milliliters. I really have to estimate. This is a graduated cylinder. And it's a very good measuring device because it's got lots of graduations compared to the beaker. And where I estimated this volume to be 8 milliliters, if I'm reading this volume, and remember we always measure read from the bottom of the meniscus, it looks like it's right at 15 milliliters. And I estimated the ones place when I was reading the volume in the beaker. If I wanted to estimate one place past what I could see for certain here with a graduated cylinder, then I would estimate that to be 15.0 milliliters, estimating that tenths place. In science, we report all of our measurements in terms of significant figures. That is, all of the digits that we are certain of, plus one final digit that is uncertain or estimated. There are a set of rules that you need to be familiar with for determining significant figures in a measurement. Rule number 1, all non-zeros are significant. So in the measurement 1,267 centimeters, we have 4 sig figs. Rule number 2, trapped zeros are significant. Trapped zeros are zeros that are in between two non-zeros. In the measurement 6,006 meters, there are 2 trapped zeros confined between 2 non-zeros, so we have a total of 4 sig figs. Rule number 3, zeros at the end of a number. If there's a decimal somewhere in that measurement, then the zeros at the end of that measurement are significant. So this measurement, 12.210 grams, would have 5 sig figs. If there is no decimal in that measurement, then the zeros at the end of that measurement are not significant. So in the measurement 1,140 miles, since there's no decimal in there, that zero would not be considered significant, and my total number of sig figs then would be 3. Rule number 4, leading zeros, or zeros at the beginning of a number, are not significant. In this measurement, 0.007 grams, since we have 3 leading zeros, we end up with only 1 significant figure. Now these zeros at the beginning of a number may not be considered significant, but they are important. They're placeholders. And for this rule, it doesn't matter where the decimal is. If there are zeros at the beginning of the number, they are not considered significant. Rule number 5 is a long one. I'll break it down here. So for adding and subtracting, our first measurement goes out 3 places after the decimal. Our second measurement goes out 1 place after the decimal to the 10th place, which means our answer is going to have to also be rounded to the 10th place. So we would express this in terms of correct sig figs as 7.1 centimeters. Rule number 6, when multiplying and dividing, the answer should be rounded to the least number of sig figs in the measurements. So in this equation, we have 2 sig figs in the first measurement and 3 sig figs in the second measurement, which means that our answer should be rounded to the least number of sig figs, which will be 2. So if I want to round my answer to 2 sig figs, it would be 5.5 meters squared. And finally, conversion factors and counts are considered to be exact. Therefore, they're considered to have infinite precision. If I count 18 students, I couldn't estimate 1 place further. I couldn't have 18.1 students. In chemistry, since we deal with matter that is really small, our measurements can also be very small. And when counting atoms, the numbers we use can get really large. Using scientific notation makes this all a whole lot easier. In scientific notation, numbers are written as a number that's greater than 1 but less than 10, and a whole number exponent. If we wanted to express this measurement, 24,000 meters, in scientific notation, and we know there's a presumed decimal right there, we would move that decimal 4 places to the left. Now we have our value for m as being a number greater than 1 but less than 10. And since we moved our decimal 4 places to the left, our exponent then is 4. Let's look at a number that's less than 1. If we are to put this number into scientific notation, we'll need to move this decimal 1, 2, 3 places over to the right so that we have our first number as greater than 1 but less than 10. Giving us 6.3 times 10 to the, and we moved 1, 2, 3 decimal places to the right, so our exponent is going to be a -3. When adding and subtracting in scientific notation, the first thing you must do is make sure that both of the exponents are the same. So I will have to change this exponent to a 3 or change this one to a 2 in order to add my m values. Let's first change this exponent to a 2. And since I'm decreasing the exponent by 1, that means that I'm going to increase my m value by 1 place. So this becomes 12 times 10 to the second kilograms. Now we add our m values together, and we get 13.6 times 10 to the second kilograms. Now we can also change this measurement to an exponent of 10 to the third. And since we're increasing our exponent by 1, we're going to decrease our m value by 1 place, making this 0.16 times 10 to the third. And when we add those m values together, we get 1.6 times 10 to the third kilograms. And so these are actually the same values. Now to multiply in scientific notation, what we would do is multiply our m values and add our exponents, giving us 2.8 times 10 to the 5th meters squared. And to divide in scientific notation, we would just divide our m values and subtract our exponents, giving us 3.3 times 10 to the 2nd centimeters.